Right. So hello everyone. Today we're happy to have Jonah here, and he's going to tell us about quantum information before the pitch. Take it away.
Thank you. All right. So today I'm going to talk about some quantum information aspects of Hawking radiation in some simple models. Let me just set up the problem. Start and very broadly. This is based on bits and pieces of some of these works that I've been working on the last couple of years. So I won't have so many details, but I'm of course happy to talk about these things afterwards. So the information problem set up is the following. So consider that we start with some pure state of matter that collapses into a black hole, or we get a black hole somehow that's in some pure state. So Hawking tells us that this black hole is going to radiate thermal radiation. The thermal states are maximal entropy states for their entropy, or for their energy. And so they really contain like a minimal amount of information. So if you consider some observer has a measuring device and is collecting all of this radiation, this observer can't really do anything to figure out what the state was of the black hole if the radiation is purely thermal. So we're losing the predictability of figuring out what the initial state was just based on measurements of the radiation. So there's been a lot of recent progress in the last few years. Mainly from the gravitational path integral. People have computed the Page curve, so which is the entropy of the Hawking radiation. So von Neumann entropy is defined as minus trace of rho log rho, where this is the quantum state of the radiation. People have computed the Page curve, which is this as a function of time. So if I have von Neumann entropy here and time here. So if we took Hawking's calculation literally and considered this to be purely thermal radiation has a volume law entropy. And so this would just go up for all times until the black hole is completely evaporated and we'll have a gas of thermal radiation. So this is a problem because at late times from unitarity, we would expect to have some pure state at late times. And an important feature of von Neumann entropy is that if you have two systems, which I'll call the black hole system, the radiation system, and they're in a global pure state, then the von Neumann entropy of the radiation should equal the von Neumann entropy of the black hole. And as the black hole evaporates, its coarse-grained entropy, described by the area of the horizon over 4G, goes down until it totally evaporates away. So what was computed was this fine-grained entropy of the radiation, and it was found that it follows this Page curve, which is consistent with unitarity, that goes up at early times and down at late times, going back down to zero, so that we have consistency with unitarity. There's one very important time in this picture, which is when this dip starts to happen. This is when the radiation starts to not look perfectly thermal anymore, and starts to purify itself so that its entropy starts to go down. So this is when the radiation entropy equals the black hole entropy. And this is called the page time. So clearly from these computations, at this late time or after the page time, your state no longer looks thermal. And there are like large corrections to this idea that the Hawking radiation is perfectly thermal. So what I'm going to talk about or focus on is actually before the page time, when it still looks like it would be thermal. And I'm going to describe two ways in which it actually is not thermal before the page time and how there is some non-trivial constant information in the state of the radiation. Okay. In case I don't finish everything, I'm going to just write my main results or the two main ideas. And they'll come from two different ideas in quantum information theory. The first is regarding distinguishability. So here, I said you can't distinguish what state you came from, given measurements on the radiation if it's perfectly thermal. So for example, if you had two different black holes that have different microstates, but they both look thermal, you wouldn't be able to distinguish them. But in some simple toy models, I'm going to compute some distinguishability measures that show that black holes may be distinguished using measurements on their radiation. At any time. Evaporation. I'll make this more precise, but the takeaway is that before the page time, you would need to make an exponentially large number of measurements, exponentially large in the black hole entropy.
That means you need exponentially many copies?
That's right, yeah. You need, yeah. And I'll get into, the details of what this means in a minute. And then after the page time, you just need one copy to be able to distinguish different black holes with high fidelity. The second part of my talk will not be about distinguishability, but it will be about entanglement, more similar to this page curve story. And I'm going to claim that there exists some time scale that I'll call t lowercase b that is less than the page time, so something that happens before the page time, when there exists significant quantum correlations within the radiation. So within the radiation. So purely thermal states, they have no quantum correlations amongst themselves. And so we're going to have to, we're going to see that there's some time scale over here that there's actually non-trivial quantum correlations.
Does that affect the entropy?
No, yeah, so it doesn't, so we get a different, we're going to compute different measures of entanglement that are more suitable to mixed states. And these will tell you about entanglement within the radiation. So now, before I had this picture of the black hole in the radiation, but the story with the second part is going to be, you take part of the radiation, so radiation 1, and you have a third part, radiation 2. And you're looking at entanglement within the radiation.
The question was, does that affecting the shape of the curve that you're drawing on the upslope?
So it doesn't really affect this entropy curve, but these more detailed description, and it doesn't affect like a curve for mutual information, like the mutual information, that doesn't change. And that the mutual information will only be affected at the page time. But these other quantities actually are sensitive to quantum correlations even before the page time.
In the first case, when you say, are you choosing some particular basis to distinguish the black holes?
Yeah, I'll write this explicitly, but basically I'll consider two different states of a black hole that macroscopically look the same, but are microscopically different. And there'll be a statement that you can construct a measurement, the OBM, that distinguishes these two states just from the measurement. So the basis of those two states. Let me get to this in a second. So in some examples, this timescale is important for other reasons. It shows up in some other calculations. Yes?
Sorry. One shouldn't be T larger than T page.
Yeah, so I think this is the surprising thing, that so even though it looks like it's perfectly thermal over here, because this is less than T page, you're getting quantum correlations in the radiation earlier than you would have expected from computations of just the von Neumann entropy.
Okay. Because there is T less than T page on both of them.
Oh, did I do something? Oh, point. Oh, yeah, sorry, yeah. T greater than T page. Yes, thank you. So this timescale shows up in the hidden Presco protocol. So if I throw a diary into a black hole and you want to know when can you reconstruct the state of the diary using just the information in the radiation. So if we do this reconstruction using something called the PETS map, this timescale that's before the page time becomes important for when the fidelity of this PETS map starts to significantly increase. Okay. And another thing about this point two, and I'll describe what these things mean more precisely in a minute, is that a quantity called the entanglement cost, which is the number of qubits you need to create a state, is much greater than the entanglement of distillation, which is if you're given the state, how many sorry, when I say qubits, I meant bell pairs. How many bell pairs do you need to create the state? It's much greater than the number of bell pairs you could distill from that same state. So this is something roughly called bound entanglement.
Did you mean to say which times EC is much bigger than ED?
Oh yeah, sorry. I meant yes, between the bound time and the page time. So it's this like interesting time before the page time. Any questions before I jump into number one?
To repeat the definition of EC versus ED.
Yes. So EC is the entanglement cost. So if you can consider bell pairs as a resource, and I say go make this state. Here's this many bell pairs. Can you do this? So it's a certain cost of creating a state using entanglement. And then there's the opposite thing is I give you the state and I ask you how many bell pairs can you distill from this state using local operations and classical communication. And these are not equal in the case of mixed states. They're both exactly equal to von Neumann entropy in the case of pure states.
Definition of easy depends on this LOCC, or this on the local operation.
Yeah. This is for LOCC. Yeah. Or else you could make anything. Okay, so let me start talking about distinguishing black holes. And to do so, I'm going to review a protocol called quantum hypothesis testing. And so this is the protocol where if I tell you that I'm either giving you the quantum state rho, or I'm giving you the quantum state sigma, what's the best you can do in figuring out what you got? And so what you're allowed to do is these generalized measurements, called the OBMs. And in the case where you're given just you know that you have one of two things. You have different measurement outcomes, and you associate one of the measurement outcomes to that you got state rho, and the other measurement outcome corresponding to, if you get the other measurement outcome, you would say that you got state sigma. So these are just two operators. You can think of them just as like projection measurements, projections that add to the identity. So n and 1 minus n. Unless these are like perfectly orthogonal, you're going to have some error where sometimes you think that you are given state rho, but you are really given state sigma. And this is the type 1 error. So this is, I think you were given state rho, but you were really given state sigma. Hope I didn't switch that around. But then there's also the opposite thing, is where you conclude that you were given state sigma when you are really given state rho. So we have the freedom as an experimentalist to, okay, if you can do whatever you want in the lab, you have the freedom to choose what the best possible M is. And so there's many ways of minimizing these errors. Probably the most natural one, the first one you would think of is just minimizing the sum of these errors over all possible measurements. And this can be shown to equal 1 minus the trace distance between these two states. And this is actually something that can be computed. So even this minimization process might seem hard, but it can be computed. It's just 1 minus half of the trace norm, the one norm of rho minus sigma. So if rho and sigma are the exact same states, you're not going to be able to distinguish them, and you're going to get a large probability, a large error probability necessarily. But if these are very different states, this thing will be close to 2, and you have very small error probabilities. You can actually explicitly construct what this measurement is. The optimal measurement, Hellstrom and Baleva. This optimal measurement is given by the sum of these two projections. Is the projection of rho minus sigma on the positive eigenspace, the positive part of rho minus sigma, and then this is like the 0 eigenspace of rho minus sigma. So this is the sum of two projectors. And that will, this particular measurement is the optimal. So now you can do much better if you're given multiple copies. So for example, if I gave you rho tensor to the n or sigma tensor to the n, you can now make a measurement on this joint state, and you could do much better. And so different distinguishability measures, probably all the ones you've heard of, have some direct interpretation in terms of hypothesis testing on how you're minimizing these two errors. The one that I'll just mention now is the fidelity, or a certain fidelity. It's the following. So if I give you n copies, I'm just putting the n there. This will upper bound this fidelity to a power, which is just explicitly given in terms of these density matrices like this. And we can compute things like this. So now to check, in some case of an evaporating black hole, we want to compute things like these distinguishability measures, and then this will say if we can distinguish these two black holes. So for this purpose, I'm going to use a simple model, this West Coast model, or PSSY, where we take JT gravity, decorated with A flavors of non-dynamical rays. And in this paper, the state they wrote down to describe, okay, sorry. And then there's also, so there's the black hole, this describes the black hole system. And then we also have a auxiliary radiation system. And we entangle the two. So this models what the state of the combined state of the radiation and black hole is at a certain time. So one possible state, or the state that they wrote down, looks like this kind of maximally entangled state between flavors. This is a certain flavor of the brain and the black hole, entangled with states of the radiation. This is the model. Here, let me just draw a picture of what the black hole looks like. We have some brain behind a horizon, and the flavors of this brain are entangled with the states of the radiation. Now, because we want to compare different black holes, we can just come up with another different state of the combined system. Simple way to do this would just be to permute the brain states. Oh, sorry, this was just supposed to be I. For an observer who only has access to the radiation, we'd want to look at the reduced density matrix on the radiation. So these reduced density matrices on the radiation, you just simply trace over the black hole system. For a state like this, and then there's an analogous state with moving this for J+1 and I+1. And so these are not exactly orthogonal in gravity if you include wormhole effects, is what they show. So this is like a gravity amplitude. This is not exactly a delta.
You wrote two twice there. Which is the second one?
Yeah.
Oh,
Chemicals.
oh yeah, sorry. These are supposed to be two different ones. I call them 1 and 2. I'll put a 1 there.
Yeah, I don't have capital size.
Oh, that's terrible. Yes, thank you. Okay, so fidelity is, we can compute it, but let me, for the sake of time, just compute like a proxy for fidelity that gives the main idea, and then I'll give the full result. So there's a proxy for fidelity that doesn't actually have an operational meaning, but it's easy to explain very quickly. And it's just the trace of rho R, just like this overlap. So between these two density matrices, divided by their purities. Trace. So if I just do this, it's very simple. We only have to compute these density matrices squared. For quantities like trace distance, we'll need to look at higher moments. I won't do that right now. But one thing to know about this is it's one if and only if rho R equals rho R. Rho R1 equals rho R2. This was computed in this 2019 paper, those authors. So just if I consider the purity, so trace of rho R squared, you get some overlap squared. And we can write this as some boundary conditions to a gravitational path integral. So this is the boundary. And we use the rules that we fill in the bulk of the path integral in all possible ways. So one way is to not include wormholes, because there's still this sum here. You don't include wormholes. You just get this first term, that's like two disconnected pieces. So two disconnected spacetimes. That connects the I and J indices, these brane indices. And then there's a different configuration that connects the two. So this is like the wormhole contribution. So we could have done one or the other. These connect these brane indices in different ways. You can see that one of the contributions gave two of these partition functions that had one boundary. I'm going to just call that partition function Z1, so it's Z1 squared. It's normalization. And the wormhole one, we'll call that Z2, is the partition function with two boundaries. It's a k squared because of the sum over indices. Okay, so this will give the purity. The important point when we're computing these distinguishability measures is that rho R1 and rho R2, they have these different brane states that are permuted by one. And so if I had done this relabeling, so this was I, J, but now this is I plus 1 and J plus 1, we're not allowed to have this wormhole contribution anymore because it would connect the J to a J plus 1, which are different flavors. So we don't allow this in the path integral. So for this term on top, we don't have this, and we only have the first term. So this was a simple exercise that gives this F tilde write it like the following: the full answer, if we include the wormholes only for the denominator but not for the numerator, is 1 over 1 plus the exponential of the entropy of the radiation minus the second Rényi entropy of the black hole. So the entropy of the radiation, I'm just calling log K. It's the number of degrees of freedom that are being entangled. And this black hole entropy, the second Rényi black hole entropy is, I'm calling minus log of Z2 over Z1 squared. So this is just like a proxy, but you can see when at early times when the radiation entropy is much smaller than the black hole entropy, this is very close to 1, but not exactly 1. So that means that you can't distinguish these black holes. And then at late times, when the black hole entropy is, sorry, did I mix that up? Oh, when the black hole entropy is much smaller than the radiation entropy, this whole thing goes to 0. You can distinguish these.
And what happens if you take the gravitational amplitude to be delta I, then my fidelity will go to 0.
If you
I just take that.
If you did this, and that would mean that you never include wormholes even for the denominator.
Exactly.
Then you would, at every single moment in time, you would have f tilde equals exactly 1. And so this means that if you don't include wormholes, you would get the analog of Hawking's answer, which says that you can never distinguish these states at early times or late times. Because you would just get rid of this term and it wouldn't even be dependent. Yeah, so one important thing is that even at early times when this is close to 1, it's not exactly 1. And so we can see that these states are not the same. And so this already hints that you can distinguish using measurements on the radiation. So I'll just give the answer for this, the full answer for this more complicated fidelity. So you can compute these other distinguishability measures either using some like fancier combinatorics by looking at these higher moments, or you can use some techniques in free probability theory. I'll just write one of the answers. So for this fidelity I wrote before, you have to look at higher replicas. You have to compute rho 1 r to the m, rho 2 r to the alpha for arbitrary integer m and alpha. But then eventually you get that the fidelity is given by just some hypergeometric functions. Now that you're computing these kind of better quantities, you don't get the second Rényi entropy of the black hole, but you get the von Neumann or the actual entropy of the black hole. And so this has some transition at the page time. So this is for, and then in the opposite regime, so after the page time, this thing becomes very small, so exponentially suppressed. I'm so f is 1 that I won't write down. Could you say again what this is?
F was the trace of the square roots of rho.
Yeah, this f is this is a square root.
So this is a computation, the PSS wide model.
Yes. Yeah. Yeah, so if you do like the full computation of something like this, yeah, then you get this answer. So this is very close to 1 before the page time, but you can see that if given enough copies, so if you're given n copies, anything less than 1 you're gonna eventually make it small enough so that you have a high fidelity of distinguishing these states. So you can check that you have to have some that are exponentially large, or S black hole minus number of copies of this state in order to distinguish these states before the page time with high fidelity.
So in the when SB is much bigger than S radiation, so we put it each time that number is close to 1, you're saying?
Yeah, so like these hypergeometric, it's like 1 plus some linear term in this.
Yeah, so it behaves like this, at least in the neighborhood when the number is small. But then how do I go again from this expression to that expression? So there's
sorry, which expression?
Yeah, because I'm still with the number of measurements. So
Yes.
There's the little n. Does it play a role?
Yeah, so what I'm telling you from this is that this quantity here bounds the error probabilities if given a certain number of measurements in this like asymptotic regime. And then I'm just computing this quantity right here.
Yeah, but just putting n equals 2.
I can choose n to be anything in this, yeah. And this holds. Yeah. And just the fact that this is, if I chose n equals 2, then I would still have a high probability of error.
Yeah, so you're taking large n. That's the result. So that's why
he's computing the thing that he's raising to the power n.
Yeah,
Yes.
Yeah.
So like 0.9 to the
Right. So okay.
If you had, let's say, 1 qubit in the radiation and I do enough measurements, then you can distinguish it between.
1 qubit, like so at the very beginning, you mean?
Yeah. So then you do it to the black hole measurements.
In theory,
You
yes.
need to measure this qubit. Perhaps there is some projection into some direction that is very different. There's a tiny difference between the two cases, and you have to do many measurements to see it. That's it. Yeah.
That's the idea. Yes.
Obviously, you're not claiming you can determine what the initial state was. If you're given 2 options for what the initial state was, you can determine which of those 2 is correct.
Yeah, that's right.
Similarly, you could have, one of your 2 options could have been an exactly thermal density metric, and the other could have been what you've actually discussed.
Mm-hmm.
You would have gotten a similar answer, I imagine.
Yeah. That's right. Yeah, that's totally right. So you have to know that you're given one of 2 things at the beginning in this hypothesis testing protocol. There's a generalization of this to if you know you're given one of any number of things, so and different distinguishability measures that we can compute bound those things. So you could say like, I know I'm given one of the e to the s black hole states or something, and then you can place similar bounds. But for simplicity, I just said you're given one of 2 things. Yeah, and okay, so in here, because this is already very small, we only need a single measurement. But that second part after the page time could already have been is already known just from these page curve computations. So in those computations, this island forms within the black hole, and so there's some region inside of the black hole that can be almost perfectly reconstructed. So this was understood. And so if you can almost perfectly reconstruct this state behind the black hole, then you can certainly distinguish these 2 different states. So this is all like before the island was formed. And so you can think of this as some small corrections to like the JLMS formula.
Would the statement be true if, suppose if you have a remnant which doesn't completely evaporate?
I don't know what to say. I don't know what to say about remnants. Yeah, I mean, all I can say with confidence is this very simple model and what I can compute. One thing I'd like to do is kind of see if this is a more general phenomenon in like other models of black holes. And there's one other model that I can actually compute things in, which is in one higher dimension, which is like a BCFT to model of black hole evaporation. So using like ADS-CFT for boundary conformal field theories, we get a similar conclusion that you need that you get this scaling for these fidelities. But, it would be nice to have a more general idea of this.
That formula, that hypergeometric, how does it come out?
Yeah, so we need to have many of these replicas because I'm computing one of these to the m and another to the alpha, where those are both integers. There's some, you can organize, so you have to sum over all possible of these kind of like wormhole contributions. I just showed the one that's just a single wormhole, but you can have these like wormholes with like 3 boundaries or any number of boundaries. And there's some combinatorics to this, like related to like non-crossing partitions that, okay, that's the best, that's not a very direct way of, I don't have a good intuition for hypergeometric functions beyond just, they come out of these counting arguments.
So, but that formula is the only thing that says that we are talking about black holes. Because many of the things that you said could be applied to any density meter.
Yeah, that's a great question or comment. And this is true. I've been focusing on black holes, but really the first computation I did was just for thinking about a completely random state, the same thing that Paige originally thought of, which is just normal quantum mechanics, no gravity, and I just take a completely random state and I partition it. And you get like these kinds of answers. Yeah, I'm just putting it into the context of black holes because it's fun. And yeah, that actually also brings me to another point I wanted to say, is that there's similar states that you can write down in just many body systems. There's some like conjectures or like some ansatses for what high energy states look like in many body systems when you partition them into 2 regions. So if you take some eigenstate of some non-integrable Hamiltonian and you look at the reduced density matrix, you can play similar games with like very similar combinatorics, and you'll find answers that show very strong versions of the eigenstate thermalization hypothesis. I wasn't planning to go into that too much detail. And okay, also similarly,
Confused now. So suppose if I take a burning coal, then how would I understand that I would require infinite amount of measurement to understand my distinguishability before I hit the page curve? Sorry, repeat. So because this calculation could be, you can do it for any system. I don't require a black hole.
yes.
Suppose I take a burning coal.
Yeah.
Then before I hit the page time, it's not so clear to me that why would I need to make infinite or infinitely large measurement to distinguish my 2 such burning coals.
Yeah, so if this is my burning coal system, and or this is the radiation coming from burning coal, that's very complicated. That's a very complicated state coming out of burning coal. And I mean, kind of the point of, I feel like a lot of this progress is to say that black holes are kind of like burning coal. Like you can, like they're unitary and you're not losing information. But yeah, there's no difference. Yeah. If you want to think about normal thermalizing systems, then you get the same answers. But it's still going to be quite difficult to reconstruct your state if you only have partial information about it. Yeah. The same thing for just any system or like some time evolution, any non-integral system. In the last little bit, I'd like to talk about this second piece, unless there's more questions on this.
When you say that up to the page time, you only need 1 copy, usually we believe that you need to make very complicated measurements in order to distinguish. So
yes.
What about before the page time? Is the statement that you need exponentially many complicated measurements?
Yeah. Good question. So I don't really say anything about complexity. I think so. The point is that you can do this in theory. I wrote down what this like Label-Hellstrom measurement is. You can construct it. This is not a simple measurement. I don't think there's, I don't think anyone would say this is a simple thing somebody could do. So I think you're right in saying that kind of before the page time, at least this construction says you can, if you do like an exponentially large number of very difficult measurements, you can do it. And after the page time, it'd still be one very difficult measurement. But at least you could do it in one shot.
The optimal procedure is likely a very complicated joint measurement on many copies, rather than many complicated measurements each on one copy. You just said it a moment ago as if you're supposed to measure many times each in one copy. You can, but that's probably not optimal.
Yeah. That's actually the reason why this is a inequality. This is actually as if you had done everything on individual copies. But there's another distinguishability measure that makes this into an equal sign, and that one may like do a joint measurement on the different copies that doesn't tensor factorize.
I think you probably said it, but I missed it. So could you explain how do you conclude you need an exponentially large number of measurements?
Yes. So I have this formula for the fidelity. It's computed from the replica wormholes. This is like 1 plus this thing, e to the s rad minus s black hole.
So there's a connection between the number of measurements and the fidelity. I guess the piece I missed is the connection between the number of measurements and the fidelity.
Oh, yes. So the fidelity for any integer n, the fidelity to this power bounds your error probabilities. So if I only took like 2 measurements, this is still very close to 1, and so your error probabilities are still large.
Okay.
But if I take this to a high enough power, then yeah.
So if you take a high enough power, then what will happen?
So if I take something less than 1 to a high enough power, then I can make it as small as I want. And I'm just saying that you have to take it to this this huge amount of power in order to make it, very small.
The Bernoulli example, your fidelity will be 1.
Fidelity will be 1.
That will be 1, close to 1.
Close to 1, yeah. But you would have to take, if you have less than half the system, it would be close to 1. But you could still take it to a high power and make it small. Okay, so now let me talk about entanglement within the radiation. I'll just draw this again. We have the black hole, and we now split the radiation into 2 pieces. So I mentioned this before, but entanglement entropy is really just a good measure of entanglement when you have a global pure state. So if I have some global pure state A, B, then the entanglement entropy of A or equals B, and that actually measures the entanglement. But if I have some mixed state, so if I had a global state on A, B, and C, but I trace over C, entanglement entropy doesn't really tell you anything about entanglement. So I'll redefine these 2 quantities, this entanglement cost, which is the number of bell pairs needed to create the state, and the entanglement of distillation using LOCC. And entanglement of distillation is the number that can be distilled using LOCC.
Are we tracing out the black hole or one of the sections of the radiation?
Yeah. Sorry. We'll trace out the black hole because we're saying we don't have access to the black hole and how much entanglement is within this radiation.
Any simply concurrence mixed system.
I forget how complex this is defined.
Okay, okay. Maybe that turns out to be similar.
So for pure states, both of these just equal von Neumann entropy, but mixed states are irreversible in the sense that entanglement cost, it costs more to make the state than you can distill from it. These quantities, you can see how they're defined. They're very difficult to compute because you need some optimization, like the best possible way you can distill things, for example. And in
what CC is, because just to say electron is rho for a given system.
Yes.
But I could use some more explanation about ED. Because if I just give you a system and you don't have access to whatever it might be entangled with, how can you distill anything from it?
Yeah, so I'm saying that if you have if you give a density matrix on AB, and I allow you to do
about A and B, but only through LOCC.
Only through, yeah, no joint operations. And then how many can you'll wind up with is some entanglement, some bell pairs between A and B, and then just some junk.
Here, A and B will be the radiation on the black hole, or 2 parts of the radiation?
2 parts of the radiation.
How would you have that, and in practicality, how would you have the LOCC? What you have in mind?
So these are, so local unitary. I don't know. You can. I don't know what people actually use.
The classical communication is for me.
I don't know if classical communication actually helps you or if you only need local operations. I haven't looked into that. That's a good question. So instead of computing these that we don't know how to do, there's 2 other quantities that are computable without optimization procedures that bound these quantities in a useful way. One of them is probably familiar. It's just the mutual information between A and B, which is a linear combination of von Neumann entropies. This upper bounds the entanglement of distillation. Or maybe it's I/2. Yeah. And then the second quantity is called the logarithmic negativity, which requires a little bit more explaining. It's the log of the trace norm of the partially transposed density matrix of AB. So if you have a density matrix, you could take the transpose on the whole system, or you could just transpose one of the tensor factors. And once you do this, this is some linear operation. It gives you, you can now have negative eigenvalues where you weren't allowed to have negative eigenvalues before. And so this measures only quantum correlations. So for example, this is an actual entanglement measure. So it's like monotone under LOCC. Well, mutual information is sensitive to both entanglement and classical correlations. So this is not like an entanglement measure, it's a measure of total correlations. But both are useful for us because the negativity lower bounds the entanglement cost and also upper bounds entanglement of distillation. There's no bound that I know of between negativity and mutual information.
No upper bound on the entanglement cost.
Sorry?
There's no upper bound on the entanglement cost.
Yeah, it should probably be bounded by like log of the dimension. Well, there are some interesting upper bounds on entanglement costs, but I won't get into it. Yeah, so these are we can compute these both using replica tricks. So similar to what I did before for these distinguishability measures. And I won't go through the details for lack of time. Mutual information, or each of these von Neumann entropes, was already computed in these previous papers on the page curve. So we just have to take some linear combination of them. And you know what can actually be done is what they do is they actually compute the full spectrum of the reduced density matrix. And by computing the full spectrum, then they can just evaluate this mutual information. So what you get is a plot like this. So if this is, if I now split the radiation into K1 and K2, or K1 states and K2 states, then multiply to the K from before, and I look at mutual information between R1 and R2. You get.
Maybe I have a very simple question, and you did explain, but why did you do this radiation 1 and radiation 2? What was the logic?
So the question in the second part that I'm trying to address is there any quantum correlations in the radiation before the page time?
So which one? So radiation 1 will correspond to what? And radiation will correspond.
So here we don't have like a, I mean, you could think of it like early and late radiation, but you can depart in this very simple model, like you can kind of just partition any way you want. There's no good distinction.
There's only one black hole, and then you're partitioning.
Yeah, one black hole, lots of radiation, and you just make some arbitrary cut.
Okay, thanks.
And if this is like a thermal state, there's no entanglement.
Yeah.
So,
and what you want to show that there is an entanglement. That is partition mind.
That there is entanglement even before the page time.
There isn't.
There is.
There is.
Yeah. So from mutual information, you can see, so you have something that's very close to zero. It's like exponentially small because this red curve is like exponentially close to this thermal entropy before the page time. And then it will grow. So yeah, I've just partitioned the radiation in half. And then it'll grow linearly at the page time. So this makes sense. This is when the radiation starts to purify itself, meaning that it's entangled with itself.
And what is giving rise to that rise in entanglement? What is how should I see this?
Yeah, so if I take some global pure state and take a very small amount of it, it looks very thermal because the rest of the system is kind of acting like a bath for it. But we know eventually the whole state is pure, so it has to purify itself eventually, and it's at this point that it starts to purify itself. So by purifying, that's the same thing as saying that it's entangled with itself. Okay, I'm out of time, so.
I saw it's a TP. Yeah, I didn't see that TP you found it.
Yes. Okay. Yeah. So it's at the page time that this happens. So let me skip to the answer, which is you can also compute the full spectrum of the partially transposed density matrix using certain calculations. And that allows you to compute this negativity if you compute this full spectrum of the density matrix. And you find something interesting that the negativity is very small at early times, and then it starts to linearly increase at a much smaller time than the page time. This is a model dependent time. This is not, I'll tell you what it is in some models, but this is a model dependent time, but it's always at least smaller than the page time. So it goes something like this. So this is like negativity.
Question, what is the horizontal axis? Increasing.
Yeah, you can think of this at like just at like time. But in the West Coast model, they model time by just making the entropy of the radiation larger.
You're thinking like,
this is like,
okay, 100 to fix, but the overall number is increasing.
Yeah. It's so if I have this thing that separates the black hole and the radiation, I'm just moving this to the right, and I'm moving it to the left, making the black hole smaller, making the radiation larger. There's no like Lorentzian dynamics in this model. Yeah. But you should think of this as just time. And so importantly, there's this region here. Okay, so let me just say what the bound entanglement time is. In some models, it's when the radiation 1/2 entropy, so this Renyi entropy, equals the second Renyi entropy of the black hole. And Renyi entropes are monotonically decreasing with their index, so this will always be before the page time.
This thing being non-zero, what does it prove about the relation between ED and EC?
Yeah, so the conclusion, so right here we see that the negativity is larger than the mutual information, which is entanglement cost is larger than this, and the entanglement distillation is larger than this. So the entanglement cost is macroscopically large, and the entanglement distillation is very close to 0.
I see.
So that's the conclusion in this interesting region.
Originally, you wrote them much bigger. Oh, where does it come from? Oh, in your board upward.
I wrote, much bigger?
Yeah.
Yeah, because the mutual information in this region is very close. It's exponentially small. While this one is out of volume law. It scales with the actual. Yeah, so that's much bigger. And so this is what we kind of loosely call bound entanglement. In the literature, bound entanglement is when entanglement of distillation is exactly 0. But this is still some large amount of irreversibility. It's in the spirit of bound entanglement. So let me stop there. Thank you.
Thanks, Jonah. Any further questions?
Maybe say one word about the PATS map.
Okay. So using, I didn't give you all the details behind this calculation, but in the PATS map, so the process we're thinking of is starting with some a state where we throw in the diary, and then it radiates, and using the state that you get, we apply this recovery map, the PATS map, called R, and to try to recover the state of the diary. And you can ask how well did this PATS map work? And you can quantify this by looking at the fidelity between the state that you get using the PATS map and the actual state of the diary. At any time you can compute this. It's
the fidelity is small before the page.
Yes, yeah. So the fidelity is very small before the page time. But one kind of an intriguing thing is that so it's very small before the page time, and it's close to 1 after the page time. But there's some new dynamics that kick in right at TB that make it grow in like a. It's sensitive to this time scale. You kind of think of it like it's like you have this kind of quantum information, this entanglement within the radiation, and I don't know. It's kind of just an empirical fact that we noticed is that this time scale also shows up here when we look at the fidelity of PATS map. It's still quite small here, so it's still not order 1. So maybe it doesn't matter. Like
Quick question. Do we have a nice form in terms of the density matrix for the EC and ED?
So these are defined using like optimizations. So it's like you're optimizing over all LOCC, which is generally difficult, and so there's not like yeah, and that's why I go and use like things that I can compute, like mutual information and negativity.
And just so irrespective of your how you model your wormhole, would you still have this relationship maintained, or would you be able to change it, alter it? Suppose maybe someone comes and tells me that I have a different way of computing this Euclidean path integral, which gives a different answer. Would I be able to switch the epsilon and I?
Yes. So well, there's certain models where this all just collapses, and they're all like that. This like pretty much is there's some certain models where like for example, if you're at like this pure page state, so like you can think of it as like an infinite temperature state, then these are essentially the exact same up to small factors. But if you go to finite energy states, you get this separation.
I guess here you consider this setup with the black hole and radiation. Would you consider other states, like let's say two intervals in a CFT, where your A and B are two intervals?
Mm-hmm.
Does this phenomenon also arise in that case if we use just the classical formula, or do you need to?
There's some outstanding confusions on how to evaluate negativity for holographic CFTs. So I mean, we can certainly compute this, but
you say,
yeah, depending on the right way to compute negativity.
So here you're really using this West Coast model to be able to calculate it.
Yeah, I'm using West Coast model in this like equilibrium approximation that's very similar that on Liu and Trev are worked out, which is you're also summing over permutations, and each permutation gives some path integral commentary.
You did this, let's say, in a CFT where you can do the calculation, for example, let's say for free fermions, I probably do it.
Yes, free fermions, you can compute both of these things.
And is it also
so like if you did like a quantum quench in a free fermion, no, these are almost identical. So it definitely depends on the dynamics of the theory.
I'm not sure I totally followed the fidelity formulas, but it seems like you apply them to, instead of considering the first like 20 qubits, you consider the last 20 qubits that come out of the black hole. It seems like that you can better distinguish the black hole with the last 20 instead of the first 20. Is that right? Maybe you haven't done that, but.
So the fidelity, I'm always considering all of the radiation. Yeah.
No, but all the radiation that came out up to a certain point, let's say.
Yeah.
But you can ask, and so you're doing time ordered. So you say, let's say 20 bits have come out and you consider those 20. Let's say you wait for all of it to come out and then you just ask about using the last 20.
Yes.
It seems like that would be a better way to distinguish them, if I understood the formula correctly.
So in this model, like there's no difference between the early and the late radiation. So
right, but in an actual black hole.
Oh, that's an interesting question of if, yeah, that I mean, I don't know the answer to that, but yeah, that's an interesting question.
The last 20 are certainly highly non-thermal, but how much they remember of the initial state is another question.
Entropy is just going to be less, so I think get that into its formulas.
I think though the entropy of them is if the last 20 I expect still look thermal if you trace everything out.
No, they're going to be less than thermal.
They're not going to be even truly thermal. When you have a black hole that's near the Planck mass, the final force of radiation is highly non-thermal.
But even
I wasn't thinking that quite that.
Even besides that, I mean, so if you draw the picture for evaporating black hole, right, there's this annoying fact that it's not symmetric. The thing you drew that it like for a random state, that's what you drew for. That's fine. Yeah. And black hole, it's like kind of has longer thing on the right because it's non adiabatic. And so if you ask about the last however many qubits, it's symmetric. You just kind of go up the curve from the right-hand side, and that's not a thermal increase. It's kind of less than the thermal increase. That the slope is different on the right half of the curve than on the left. So since its entropy is less, I think your formulas then mean that it's more useful to use the last set of radiation if you wanted to distinguish. I mean, it's a different question than you're asking.
Yes, that might be true. I don't know. I haven't thought about that actually. That's a good question.
All right, let's thank Jonah again.